Let's examine a particular type of series that's going to come up over and over again in our studies in the next few weeks. These are geometric series. And here's an example. The sum as n goes from 1 to infinity of 3 over 2 to the n. Let's start by exploring some of the aspects of this series. Let's try writing out the first few terms. So n starts at 1. What is 3 over 2 to the 1? Well, that's just going to be 3 halves, right? Plus, the next term, when n becomes 2, we'll have 3 over 2 squared, that's 4, so 3/4. Our next term will be 3 over 2 cubed, which is 8, so 3/8, plus 3/16, plus 3/32, plus etc., forever. Notice that the terms that we're adding up here are getting smaller and smaller and smaller because the denominators are getting bigger and bigger and bigger. So one important thing about this series is that if you look at any one term, let's just say a2, then divide by a1, well, that's 3/4 divided by 3 halves. If you simplify that, you're going to get 1/2. If you look at a3 divided by a2, that's 3/8 divided by 3 halves. Make that division mark bigger there. Again, you get 1/2. And in particular, you can always multiply each term by 1/2 to get the next term. So to get from 3 halves to 3/4, you'll multiply by 1/2. To get from 3/4 to 3/8, you'll multiply by 1/2. To get from 3/8 to 3/16, multiply by 1/2. And that is true all the way down the line. That is true for every single pair of successive terms in this series. What we could say here is that 1/2 is a common ratio meaning that you can always multiply an by 1/2 to get the next term, which is an plus 1. That is true no matter what n is. You can multiply a1 by 1/2 to get a2. You can multiply a2 by 1/2 to get a3, and so on. This is the key characteristic of what we call a geometric series. Let's look at the definition in particular. So, by definition, a geometric series is a series in which each term, an, is a fixed multiple, we'll call r usually, of the previous term. And that r is called the common ratio. It's the ratio of one term over the previous term. And typically we can write out a geometric series by supposing, let's suppose first of all that our first term is a. Some number a, I don't know what the number is, I don't care. Plus, the next term needs to be that common ratio of a. It needs to be a multiple of a, and it's going to be a times r. Now the next term we should be able to get by multiplying the previous term by r again. So we have ar. We're going to multiply it by r again. So what is that really? That is ar squared. The next term we should be able to get by multiplying the previous term by r. That will become plus ar cubed. And the next term is plus ar to the 4th, and so on forever. So the terms in a geometric series consist of some initial factor there, which we'll call a, which is always what the first term is, times r to a certain power, and that power is going to increase as you go down the line, as you look at successive terms here. So how can we write this in our sigma notation here? We'll have a sum. Now, you can, when you're writing out a series, you can start n at 0 or 1 or any other place that you want to start that's convenient. It's actually pretty convenient to start n at 0 for a geometric series, but our textbook likes to start with n equal to 1, and I want to be consistent with that. So we're actually going to start with n equal to 1, and it's not that big of a deal. Let's let n start at 1 and go to infinity. Now, what is the formula that we need to write for our terms for our generic geometric series? Well, there's going to be an a in there, certainly. And the problem I have is that when n is 1, when n is the starting term here, there's no copies of r. So we are going to have to multiply by r, but the question is, what is the power on the r going to be? And when n is 1, there's actually no r's. The power on the r would be 0. When n is 2, n equal to 2, when n is 2, the power on the r is 1. When n is 3, the power on the r is 2. When n is 4, the power on the r is 3. So what is the power on the r for any n? The power on the r is going to be n minus 1. And this is the generic formula for an arbitrary geometric series. The sum, as n goes from 1 to infinity, of a times r to the power of n minus 1. And anything that is in the form of a geometric series, you can always write it in this form and identify what the a is and identify what the r is. Let's look at some more examples. Here's another example of a geometric series. Here's another example of a geometric series. The series 10 minus 4 plus 8 fifths minus 16 25ths plus 32 over 125 minus the next term, and so on. Now, of course, if you only see finitely many terms of a series, you can't guarantee that you know what the rest of the terms are. But let's suppose that we know that the rest of the terms are going to follow the most obvious pattern. In fact, notice that there is a common ratio here, because negative 4 over 10, that is a2 over a1, is equal to negative 2 fifths. And a3 over a2, that is 8 fifths over negative 4, also turns out to be negative 2 fifths. And a4 over a3 is negative 16 over 25 divided by 8 over 5. That is, again, negative 2 fifths if you work that out. And the next term works the same way. A 5 over a 4 will also turn out to be negative 2 fifths, and so on. So we can get from 10 to negative 4 by multiplying by negative 2 fifths. We can get from 4 to 8 fifths by multiplying by negative 2 fifths, and so on, and so on. So our r here, our common ratio, is actually negative 2 fifths. It is okay to have a negative value for r. And in a geometric series in which the r is negative, you will see that the sign of the terms alternates back and forth. Positive, negative, and so on. You could even start with a negative term for the first term if you want to. Speaking of which, what is our a? A should always be exactly the first term. Well, our first term is 10, so there we go. A is 10. So, what is the actual expression that we should write in sigma notation for our series? The sum as n goes from 1 to infinity. Again, you can write a geometric series starting at 0, but if you start your n at 0, you'll end up with a different formula for the expression here. I'm going to be consistent and start with n equal to 1 because that's what the book is usually doing, and let's just be consistent here. So, the formula should be the sum as n goes from 1 to infinity of a times r to the power of n minus 1. Our a is 10, so I'll put a 10 here. And then our r is negative 2/3. Put that in parentheses because that whole thing is going to the power of n minus 1. That is our formula. And because it's possible to find a formula like this that works, because it is possible to find an r that is a common ratio between each of the terms, this is a geometric series. Let's look at one more example. Here's another series. The sum as n goes from 1 to infinity of e to the n over 12. As always, if we want to, we can write out the first however many terms we feel like of this series. N is going to start at 1, so we're going to have e to the 1, which is e over 12. E over 12, whatever that is. The exact value is e over 12. If you wanted to put it into a calculator and get a decimal approximation, you could do that, but that would be an approximation. And it's really important when we're looking at series to distinguish between exact values and approximations, because after all, for a lot of series, you can approximate the value of the infinite series by taking a finite partial sum of that series, and we care about the difference between those partial sums and the exact value of the series in the end. So this is not a time for getting decimal approximations. This is a time for using exact values. So our first term, when n is 1, is e over 12. Plus our next term, n becomes 2, that's going to be e squared over 12, plus e cubed over 12, plus e to the 4th over 12, and so on, plus etc. Okay. Now, is there a common ratio here? Is there an r that we can distinguish? Well, yes, there is, it turns out, because what can I multiply by e over 12 to get e squared over 12? I'm just going to multiply by e. What can I multiply by e squared over 12 to get e cubed over 12? I'm going to multiply again by e. What can I multiply e cubed over 12 by to get e to the 4th over 12? Multiply by e, and so on. So our r here is e. What is our a? The a is always the first term. So a is e over 12. So if you want to, you could actually write this series in an equivalent form. The sum, as n goes from 1 to infinity, of a times r to the n minus 1. Our a is e over 12, and our r is e, and that's to the n minus 1. All I've really done there is basically take one of the copies of e out of e to the n. Now, e times e to the n minus 1 is just giving us e to the n again, which is what we started with. So it's very clear that this formula is the same as the one we started with. But now it's more easy to see that our a is e over 12 and our r is e. Something interesting to note here is that our terms in this series are not getting smaller and smaller and smaller. They're actually getting bigger and bigger and bigger. Because e is a number bigger than 1, e squared is bigger than e, and e cubed is bigger than e squared, and e to the 4th is bigger than e cubed, and so on. And even if you divide all of those things by 12, it still remains a fact that the higher powers of e give you bigger numbers. So our terms here are getting bigger and bigger and bigger. What is that telling us about the series? If you're thinking that this series diverges, that there is no finite sum that it comes to, you're right. And we'll look at that in just a moment. Let's look at one more example of a series here. Let's look at the sum as n goes from 1 to infinity of negative 1 to the n over n squared. And as always, we can write out the first few terms if we want to. You don't have to write out the first few terms. If you feel that you have a good sense of what this series is doing without writing out those terms, that's fine. I like to write them out sometimes because I like to remind us that what we are talking about is a sum of a bunch of numbers, an infinite list of numbers, in fact. And I don't want to get so hung up on this formula here that I forget what's actually going on. We are just adding up some numbers. What numbers are we adding up? Well, n starts at 1, so negative 1 to the 1 is negative 1, and we're going to have negative 1 over 1 squared, which is 1. That's actually, therefore, just negative 1. What's the next term? Well, now n becomes 2. Negative 1 squared is positive 1, so we're going to have a plus, and that's going to be a 1 over 2 squared, which is 4. Now n becomes 3, so negative 1 cubed is negative 1 again. We're going to have a minus here. And that'll be 1 over 3 squared, which is 9. And then we'll have plus 1 over 16 and minus 1 over 25 plus 1 over 36 minus etc. Going on forever. Now, we've already seen that some geometric series have this alternating signs of our terms here, and it's called an alternating series when the terms are alternating back and forth, positive, negative, positive, negative. We've already seen that. That would mean that your r was negative in that case. However, is there actually a common ratio for these terms? Well, we could take a2 divided by a1 and see what we get. That's 1/4 over negative 1, which is negative 1/4. Now we could try a3 over a2. That is negative 1/9 over 1/4. That gives us negative 4/9. Now, 4/9 is not the same thing as 1/4. In fact, negative 4/9 is not the same thing as negative 1/4. Right? If you took a4 divided by a3, you would end up with 9/16, negative 9/16, in fact, which is, again, not the same thing as negative 1/4 or negative 4/9. There is no common ratio. The ratio of one term over the previous term is not consistent. So, this is not a geometric series. Which is perfectly okay. It's a perfectly fine series in its own right, but it's not a geometric series, which means that all of our analysis that we are going to try and do for geometric series doesn't work for this series. And we will have to analyze this series in other ways using other tools from later sections of the textbook.